Hello again, my name is Paul Wilson and I'm here with my colleague David Clement. We are the engineers in control. This is the 14th talk in our series, Control Systems 101. In talk number 14, we are going to review the first 13 talks. The reason for this is that this is a natural break in the sequence, and it is a time to catch our breath before we move into the more serious theory and a bit of heavy mathematics. In talk 15, we should be starting to look at control loop behaviour and system stability. So far, after the basic introductions, we looked at a basic process control loop and identified the terminology we use: set point, process variable, measured variable, and process loads and process disturbances. Then we went through the fundamentals of process dynamics, and we understand that all dynamic systems behave in an identical fashion. We looked specifically at energy loss through friction or heating, kinetic energy which opposes change, and potential energy which stores energy by charging up. Then we extended dynamic behaviour through the development of differential equations. And I showed you this chart which gives you the differential equation sources for the various types of energy. And then we showed you how to use Heaviside's operator method to derive transfer functions. This then led us to an understanding of complex frequency S and how it encapsulates all the dynamic behaviour in terms of exponential curves and sine waves. That led us to the concept of a transfer function, which is the fundamental concept of control systems theory. It is also the approach that makes control system design and troubleshooting very straightforward, provided you have these skills. In order to practice the use of transfer functions, we resolved transfer functions in series and then transfer functions in parallel. We then related transfer functions in series to a practical and very commonplace example in the process industries, the motor and pump set. And I showed you that we can simply combine the transfer functions of the motor, of the pump, and of the fluid flow. Once we had looked at the motor and pump set, we designed a feedback control loop to control fluid flow rate using a motor and a pump. Finally, we resolved the control loop transfer function into a single closed-loop transfer function. And we met the concepts of the forward path transfer function and the feedback path transfer function. We named the open loop transfer function and the closed loop transfer function. You remember this equation, that the closed loop transfer function is G over 1 plus GH, and this is a very important equation to remember for control engineers. What we have covered so far lays the foundation for the serious control theory. Next we shall look into the step responses using the Heaviside step function. Then we shall learn the Heaviside partial fraction expansion. Later, we shall move into system stability analysis and have a close look at steady-state error and the sources of error in control loops. These are all important considerations for when we move into the realms of controller design. So next time, in talk number 15, we shall start looking at step responses of dynamic systems and control loops. We shall begin with a simple first-order system which has an exponential step response. So we hope you derive something useful from the first 14 talks, and we hope you will join us again for talk number 15. The engineers in control are Dr. Paul Wilson and David Clement. You can find out more about us at www.engineersincontrol.com. Unless explicitly stated, all content in this video is original and is copyright 2022 by Dr. Paul Wilson and David Clement. All rights reserved.